subtopic 4.6, Torque on a Coil. In semester 1, you have learned about torque, which means the tendency of an object to rotate when there is a force acting on it. For this case, we are dealing with magnetic force that makes the coil which carrying a current to rotate in the magnetic fields. Let's go details on how it's happened. Consider a rectangle coil which carrying a current in the presence of a uniform magnetic field that parallel to the plane of the coil as shown in the figure. Okay. So the current in the coil flow in the clockwise direction. The coil has four sides. Side 2 and side 4 are perpendicular with the magnetic fields, but for side 1 and side 3 is parallel with the magnetic field. You have learned previously in subtopic 4.4 where a current carrying conductor is placed in a magnetic field, magnetic force will act on the conductor. So, same goes here. So the green arrow represents the direction of current. The blue arrow represents the magnetic fields. According to the equations, FB equals BIL sine theta, where the theta is the angle between the current and the magnetic fields. So we can see that side 1 and 3, the angles is 0 degree and 180 degree respectively. So no force is acting on the wire because sine 0 degree and sine 180 degrees is equals to 0. For side 2 and side 4, we can see that the current flow is perpendicular with the magnetic fields. So the angle theta is 90 degrees and there will be a force acting on the wire. So by using the right hand rule, we can determine the direction of the magnetic force acting on the both sides of the wire. So why don't you all try? Have you tried? Okay. From the top view, it shows that both magnetic force is in opposite directions. As a result, the coil will rotate in clockwise directions. We can determine the torque produced by using the formula torque equals NIAB sine theta, where tau is represent torque on the coil, B is the magnetic field strength, the I is the magnitude of current flow in the coil, N is the number of turns, A is the cross-sectional area of the coil, and theta is the angle between magnetic fields B and the normal of the coils, as we call as vector area A. So if the coils is parallel to the magnetic fields B, the torque is maximum because the theta is 90 degrees. Where coil is perpendicular to B, the torque is 0 because the theta is 0 degrees. So torque produced in a coil does not depend on the shape of the coils. It only depends on the value of number of turns, the magnetic field strength, the magnitude of current, and also the cross-sectional area of the coils. So for working principles of moving coils, we are going to watch a video. So in this video, it will show you where the principles or the concept of torque is used in the principles of moving coil galvanometer. Let's watch.
A moving coil galvanometer works on the principle that a current-carrying coil placed in a magnetic field experiences a torque. On your screen, can you see the basic construction of a moving coil galvanometer? It consists of a permanent magnet, a coil, wound around a soft iron core. The axis of the core is fixed and attached to a pivot, in turn attached to a pointer through a spring. In order to use the galvanometer, it is attached, as you can see, in the circuit. On switching the circuit on, the current flows through the circuit. A torque acts on the coil due to the magnetic field, and that causes deflection in the spring and therefore the pointer. The torque is equal to NIAB, where N is the number of turns of the coil, I is the current in the circuit and thus the coil, A is the area of the coil, and B is the strength of the magnetic field. If small k is the torsional constant of the spring and phi is the deflection, we have k phi equals NIAB. The deflection and the current are thus related by the expression phi equals NAB by K into I. And see carefully, this quantity in the bracket is constant for a galvanometer. Thus, using the deflection, we can obtain the current in the circuit.
Okay, class. Have you saw the video that shows the working principles of a moving coils in the galvanometer? Okay, so that's for now. See you later. Bye.